In the vast expanse of cosmic history, few moments are as pivotal as the birth of the first stars. These celestial pioneers, flickering into existence between 200 and 400 million years after the Big Bang, didn't just illuminate the darkness, they fundamentally reshaped the universe as we know it. Today, we stand on the precipice of a new era in astronomy, one that may finally allow us to glimpse these elusive objects. To understand the significance of these first stars, we need to journey back to the early universe. After the Big Bang, the cosmos was a soup of hydrogen and helium with trace amounts of lithium. As this primordial gas cooled and clustered under the influence of gravity, it set the stage for an event that would change everything: the birth of the first stars. These first-generation stars, often called population 3 stars, were unlike anything we see in the night sky today. Massive and incredibly bright, they could reach up to 300 times the mass of our Sun and burn 10 times hotter. Their formation marked the end of the cosmic dark ages and triggered a process called reionization. Reionization was a cosmic makeover on an unimaginable scale. The intense radiation from these first stars stripped electrons from the surrounding neutral hydrogen, creating a sea of ionized plasma. This process fundamentally altered the composition and properties of the intergalactic medium, setting the stage for the universe we observe today. To fully appreciate the uniqueness of these first stars, we need to understand stellar populations. Astronomers categorize stars into 3 main groups. Population 1 stars, like our Sun, are relatively young and rich in heavy elements. They're the cosmic youngsters, born from gas clouds already enriched by previous generations of stars. Population 2 stars are older, with fewer heavy elements. These are the middle-aged citizens of the cosmos, formed when the universe was already a few billion years old. But the holy grail for astronomers is population 3, the very first stars, composed almost entirely of hydrogen and helium. These are the ancestors of all stellar generations that followed. The life cycle of these population 3 stars was dramatic and brief. Due to their enormous size and lack of heavy elements, they burned through their fuel at a prodigious rate. While a star like our Sun can shine for billions of years, these cosmic giants lived fast and died young, lasting only about 5 million years. Their deaths were as spectacular as their lives. Many exploded as supernovae, spreading the first heavy elements across the cosmos. This seeded the formation of subsequent generations of stars and eventually planets like Earth. We owe our existence to these primordial stars. For decades, the first stars have been theoretical constructs, beyond the reach of our most powerful telescopes. But that's largely changing, thanks to the James Webb Space Telescope, or JWST. Launched in 2021, JWST represents a quantum leap in our ability to peer into the early universe. Earlier this year, astronomers reported a compelling discovery. Using JWST to study the outer reaches of a very distant galaxy called GNZ11, they found potential evidence of first-generation stars. While this finding is still tentative, it represents a major step forward in our quest to observe these cosmic pioneers. The search for first-generation stars is closely tied to another cosmic mystery, the origin of supermassive black holes. These cosmic giants, found at the center of nearly every galaxy, pose a significant puzzle for astronomers. Observations have revealed fully formed supermassive black holes in the very early universe, seemingly far too soon for them to have grown to such enormous sizes through conventional means. This problem has led scientists to revisit their models of the first stars. Recent computer simulations suggest a possible answer. Some of the first stars may have been even more massive than previously thought, perhaps tens of thousands of times the mass of our Sun. These hypergiant stars could have collapsed directly into massive black holes, providing a potential explanation for the early appearance of supermassive black holes. While we can't directly observe these ancient stars with current technology, astronomers are developing innovative methods to detect their presence. One promising approach involves analyzing the spectroscopic fingerprints of distant galaxies. Spectroscopy involves splitting light into its component wavelengths, creating a unique fingerprint for different elements. By studying the spectra of distant galaxies, astronomers look for signs of ionized helium, a telltale signature of the intense radiation produced by first-generation stars. Another exciting avenue of research focuses on tidal disruption events, the spectacular flares produced when stars are torn apart by black holes. The unique properties of population 3 stars, particularly their lack of heavy elements, could make these events distinctly identifiable. When a star passes too close to a black hole, the immense gravitational forces can tear it apart. This creates a brilliant flare of light as the star's material is heated and accelerated. For a population 3 star, this process would unfold differently due to its composition, potentially creating a unique light signature that astronomers could detect. While much of the search for population 3 stars focuses on the distant universe, some researchers now suggest that remnants of the universe's first stars might be hiding much closer to home. Recent surveys have identified numerous stars in our own Milky Way with extremely low levels of heavy elements, hinting at a possible connection to the earliest stellar generations. One such star, named SMSS J1605-1443, discovered in 2018, contains only 1/millionth the amount of iron present in our Sun. While not a true population 3 star, it's likely a direct descendant, offering valuable clues about the earliest epochs of star formation. As we look to the future, new technologies promise to revolutionize our search for the first stars. Upcoming projects like NASA's Nancy Grace Roman Space Telescope and ground-based observatories like the Extremely Large Telescope in Chile will push our observational capabilities even further. These new instruments may allow us to detect the faint glow of the very first galaxies, potentially revealing population 3 stars in the process. They could also help us better understand the process of reionization and the formation of early cosmic structures. The quest to understand these cosmic pioneers is more than just an exercise in astronomical archaeology. It touches on fundamental questions about the nature of our universe. How did the first complex structures form from the primordial soup of the early cosmos? What role did the first stars play in seeding the universe with the elements necessary for life? How did the first supermassive black holes form and grow so quickly? As we continue to push the boundaries of astronomical observation and theoretical modeling, we edge ever closer to unveiling the universe's first lights. Each new discovery, each refined model, brings us a step closer to understanding our cosmic origins. The hunt for population 3 stars is more than a search for ancient objects. It's a quest to understand the very foundations of our cosmic history. As we peer deeper into space and further back in time, we're not just observing distant stars. We're uncovering the story of how our universe became the rich, complex cosmos we inhabit today. In the grand tapestry of cosmic evolution, the first stars represent a crucial thread, one that we're now finally on the verge of grasping. The next few years promise to be an exciting time in astronomy as we continue our relentless pursuit of the universe's earliest luminaries.